So we've been looking at partial derivatives, and we kind of understand how to take partial derivatives with respect to x and with respect to y. Now, an interesting generalization is to ask, what's the rate of change of a function in some direction? So suppose that you have f of x, y given by this surface here. You know the rate of change of f with respect to x, for example, this arrow is in the x direction, and you know the rate of change with respect to y. However, you might be interested in the rate of change with respect to some arbitrary vector u. In order to find what this directional derivative is, we need to introduce a couple of concepts. Namely, we need to introduce the concept of a gradient vector. And to do that, we need the concept of the gradient operator. We've seen some operators before. This is just yet another one. The gradient operator is denoted with this triangle shape. Its name is not upside down triangle, its name is nabla. Sometimes del. Sometimes it's just read as grad, but that's a bit naughty. Grad is a vector. And as such, it's often given twiddle underneath, or it's sometimes given an arrow as a hat. The operator itself is the first partial derivative and the second partial derivative, or the partial derivative with respect to the next coordinate. And it's got all the coordinates in there, right? So if you've got a two-dimensional function as we're describing here, we'd only have two components. If we had a three-dimensional function, we'd have three components. Remember that the operator is looking for something to differentiate. These don't do anything until they're applied to some function. So this is our vector operator. Applied to some scalar function. And that is equal to, obviously, just so if you like, this grad, we call this grad of f. This grad of f, if you like, is information about the derivatives in the x and y directions all over this function bump here. We've got essentially a paraboloid here, it's upside down. So let's roll with this as our function. The grad of our function is then df dx. Y is a constant, so that gives us minus 2x. When we differentiate with respect to y, x is a constant, so we're left with 2y, like that. That is our gradient vector. It's a two-dimensional function, so we have a two-component vector. we can now go and work out what the rate of change in a certain direction is. So I'll use these little x hat, y hat vectors as unit vectors, that is, vectors of length 1 in the x direction and the y direction, respectively. Right, if anything's got a hat on it, that means it's normalized to be length 1, or unit length. We define the directional derivative, that is, the rate of change with in the direction of a vector u, as grad f dot u hat. Now, obviously, that's a scalar quantity that just reflects the rate of change in the direction we're interested in, the total rate of change in the direction we're interested in, by resolving the components of the vector. So let's work through an example. Okay, so we've got a vector 1, 1, and we want to know the directional derivative with respect of f with respect to this vector. The vector u is currently not a unit vector. It has length square root 2. We must firstly and always normalize our direction vector. So if you like, step 1, normalize this u. So we work out the length of u. So the length of u, you'll recall, is just the take each component, square them, add them up, take the square root. It's the Euclidean distance. So u hat is equal to u divided by the length of u. That's how we normalize a vector. Oops. Two, we got to calculate grad. We've already calculated grad of this thing, but we'll do it again. Differentiate f with respect to x, get minus 2x. Remember that y is treated as a constant, so it disappears. Differentiate y with respect, differentiate x with respect to y, get minus 2y. Step 3, you dot these two things together. I don't usually bother putting the twiddle on grad, on the grad operator, the nabla. So when we dot something together, that means we take this component, we multiply it by this component, we multiply the x components together, we multiply the y components together, and we add them up. So this is the directional derivative of f with respect to u. You'll notice that this is a function of x and y. So no matter where we are on our paraboloid, right, we can say if we're here, we've got an x, we've got a y pointing in like that, we've got u going that way. Doesn't matter if we're there or we slide down here, right, or we move up to here, we can always evaluate this directional derivative at any point we happen to be interested in, because this thing happens to be a function of x and y.